Thank you for Dr. Mekta and Dr. Muhammad for inviting me to this event. And actually, I'm very amazed about your campus. Very beautiful, very beautiful. And I noticed that you are distinguished students as well, because only 1 out of 10 or even 1 out of 100 will be allowed to enter this university. So I'm very honored to be able to present the lecture in front of you. So I also encourage the interaction, your interaction with me. So in case that you don't understand the content of the presentation, just let me know. Just raise your hand and ask a question. All right. So in case there is not enough time in the lecture, just approach me and discuss with me after the lecture, or even after the class. All right. Okay. So this will be the schedule of the classes. We have 2 lectures from 8:30 to 9:30 and they will break between 9:30 and 9:45. Then after the second class, we will have the follow-up lab. All right, okay. And today we are going to see the power of the sun. So we are going to conduct our lab outside the auditorium. Okay, so this is pretty much the first day, the progress of first day, and the second day, third day. So you don't have to worry about that because the handout will come in probably in 30 minutes. But before we go into the real lecture, I'm going to show you some myths. Okay. So since this is not a formal class, I use transparencies that I was presented in some other places. So there's Chinese characters. Don't mind that, because your lecture handouts will be all English. All right. So I just want to talk about man, human. As a human beings, starting from very early years, worship the sun. No matter which culture you belong to, our ancestors worship sun. This is a direct linkage, the direct feeling that sun gives us the power. All right, and you know, people, men, be able to survive up to today is based on our capability of a connection with our environment. All right. So the intuition is very important, because intuition sometimes might be correct. All right. So if nowadays we are going to think about the solution of lack of resources, like in our country, Taiwan. We don't have natural resources like you. So we are thinking about what is a solution for obtaining energies other than from the oil. All right, so we directly thinking about the solar energy. Not because we are more smarter, it's because as a human being, we know that is a total solution. That is the final solution for the energy, because the energy in any form, wind, solar, and the hydrogen, chemical energy, biochemistry, actually it's all coming from the solar energy. So I'm going to tell you something about the God, about the solar things. You know, in Egypt, a god called Ra, or I don't know how to spell that. It's right. Yeah, they worship the sun, and somehow there's something like there's a bird. The head is like a bird, like an eagle. I know, and then snake. I think this represents the sun. It's very direct. We can direct linking this figure to the sun. And this is the bird. All right? And they take the ship. They take the ship surrounding the universe from the morning till the dawn. And they take another ship from the dawn, from the evening to the sunrise. Oh, they take the ship is called Manjet and Muscat. Two ships that are sailing around the globe. Somehow, I think they know the Earth is round. It's not, because they can use the ship to take turn and doing the daylight and the night. All right. And somehow this is related. All the cultures are in some sense related. Let me show you. And this is Greece, from the Greek myth. The Helios, the sun, the god of the sun, takes the chariot, sailing in the universe. All right, and they guide the sun in the universe, so we have day and night, something like that. Okay, so it's very similar, very similar. All right, we can even have, this is a picture found in a cup, something like a container. There's something saying that it drives the chariot throughout the universe. So at the daytime, it's very bright, and when the night, it can become to the other world, so it's become dark. All right. And this is some god in this area. I'm not sure if there's a god related to, or very familiar with omen. I'm not sure. So if you can provide me the information, I will put in my PowerPoint in the future for future references. This god named Mitras. And actually, this Mitra, this god, now become one of the gods in China that we call the Mila Buddha. Somehow it's go to the Buddhist area, and then later on become Chinese god, you know. And this also has this symbol, like a rays coming out from the sun. Huh? Sun shape, yes. Yeah, so actually the culture is not really isolated in this sense. We are really a group, the same group as a human being. We are related. This god is Aryans. I think it's Aryan peoples. They are worshiping this god. And in Iran, Aryan people and Indian people, after they separate, they have different shape of the god. And one comes to China and become Mila Buddha. And this is a god in India. Okay, and in their book, they also take this chariot running in the universe, so shining the world. All right, and it becomes the god in Buddhist. And this is found in the carving in China, one of the shrines in China. Okay, so can you see there's a chariot at the bottom of the figure? All right, and there is a round shape, like a tree, you know. But I believe this is the image of the Earth, because in Chinese mystery, they say the sun is actually coming from the bird. Okay, and at the very beginning, there are 9 birds hiding. They are surrounding the earth. So when the God cannot control the flight of the bird, sometimes it produces too much heat. So human will suffer. So later on, there's a person called Hou Yi, use the arrows to shut down 8 crows. Actually, this crows, 8 crows, and remaining only 1 crow. Then this 1 crow will function smoothly. So become nowadays we are not suffer from the too many suns. All right. So this is a myth that we know in China, but it's very amazing because even for me, I didn't notice this picture until recently because of the internet. I can find the information much more easily than before. So I finally found this, and this somehow related to Middle East culture or Egyptian culture. So I believe several thousand years ago, we are all the same family. So those myths can be connected. Okay, so since we have the same idea that the total solution, we are the son or the daughters of the sun, we are living because we are able to live here because of sun. So we should find the solution from the sun. Okay, so sun is the source, any source of any kind of the source, the form of the source. Now, we want to know how the consumption of the energy that human used recently. So this is probably the number that we need to remember. Exajoules. Exa is 10 to the power of 15. Yes, 10 to the 15. So 10 to the 15th times 500 will be the yearly annual consumption of the energy for human beings. Well, that is a very big number. Okay, and it can be divided by like coal, crude oil, natural gas, nuclear, hydro, biomass, and other kind. Actually, the solar, wind, the geothermal is very low because we are not using solar cell efficiently. So it has been wasted. The sun irradiates its energy towards the Earth. Then it got dissipated to the darker universe. So human did not use the solar cell very efficiently. So it only accounts for very low percentage of the energy that we are using today. Okay, so this is 500 exajoules. Okay, so this is like the picture. Okay. Later on, previously I was talking about 500 exajoules. Actually, it is produced by the power, 174 petawatts. Peta means 15. So exa is not. Giga is 10 to the 9th, right? Then tera is 12. Peta is 15. Then exa is 18. Okay, so I need to change it. I said wrong. Previous exa is 10 to the 18. Okay, so watt means second. The energy, joules per second. Every second there will be 174 petawatt shining toward the Earth, and it's constantly shining the Earth. And we have the day and night. That is because our Earth is circling around. So it's not the radiation. Radiation is a constant. It's constantly give Earth that amount of the power. All right? And in this 174 petawatt, 89 petawatt assault by the surface. So this is what we really able to use. The rest of the power has been reflected by atmosphere or assault by the atmosphere and the loss in the space. Okay? So there are that amount of energy coming to the Earth. So we can use. If we are not using it, then it will be radiating back to the outer space. All right. Okay. So you might need to remember this number, and we'll relate this power to the energy, annual energy of consumption. Okay, so this is you do the very good math. So I didn't go to detail. You just need to take the picture or just write it down. So it's a very easy calculation. Like if power is 174 petawatts, it will be equivalent to 5487269 exajoules. Exajoule. Exa is 10 to the 8 exa.
100,000 tera.
Tera.
1,000 tera.
Tera. So I write it wrong. Is that? Because this will be equivalent to 500 exajoules. So I may write it wrong. This may be tera. This number will be this number. All right? So this number will be exajoules. This number will be exajoules 500. All right. So I'll check with that later. This number will be around 500 exajoules per year. All right, I'll check with that. Then it will be correlated to the flux of 1,367 watts per millimeter per meter square. That is the irradiance of the sun. If you now go outside, you are suffering this number, around 1,000. Around 1,000. So it's very easy to remember. It's like now we have simulated solar light. We are setting the standard as like 1,000 watts per meter square. This will be similar to the irradiance of the sun. All right. Okay, I'll check with this number later. I will give you back later. So we have the standard called M1. M1 means it's 1040 watt per meter square. Okay, so I may not write it wrong because this is the solar energy that the sun provided. So actually, I'm not writing it wrong. The 500 that I presented earlier before is human consumption. All right? So this is correct. this is just simply by converting the power to the annual energy that the sun gives us. And the 500 is human consumption. So there's several orders of difference. All right? So that means sun did not give up us. They still reserve a lot of energy to use for human to use in the future, in several thousand millions years to come, as long as sun is here. All right? Compared with reserves or natural resources in Earth, that is limited. That the energy problem may not happen in our lifespan, may not be happening for our children or grandchildren. Maybe not problem, but eventually, after 100 years, 200 years, eventually our human will facing the lack of, for example, oil, coal, some problem. So, but we are safe. We are more comfortable now because sun provides this energy. So we are using only portions of energy so far. Even now we say that we are using a lot of energy. Actually, it's only fractions of the sun that the sun gives us. Okay, so this is energies, solar energy that we calculated from the previous page. And this is the global energy consumption in terms of power, or in terms of energy per years, or in terms of energy at different units. Watt per hour. Watt per hour is a power company that charges the unit that charges money. Okay. In Taiwan, there's watt per 1,000 watt or 1 kilowatt per hour means 1 degree of the electricity. All right. Okay. Yes.
500. What that mean for us? What we get it from the solar panel or?
No, this is a human consumption. Nowadays, this 500 is supplied by coal, oil, wind, solars, and even the power plant is nuclear power plant, supplied by all the firms, and they provide this 500 for human use. And actually, solar energy did not account many. You see? For solar, wind, and geothermal altogether, they only account for maybe 10 exajoules. All right? But actually, the sun can give us that many exajoules per year. So we are not using the sun at all. All right. So I think that this is more related to the Taiwanese situation locally. So I will skip up the files, then I'll go to the main course of today's lecture. Okay, I will mention this later on in another course and in English, so you don't have to worry about that. That's I just want to give you a very special flavor about the idea. And actually, you see the solar irradiance, I need to find the pictures for Oman. Actually, Oman is very good for developing solar energy. The solar energy is much stronger than anywhere in the world. I don't know why. Here is Taiwan. Let me introduce you. India, okay, and Southeast Asia. And now going from Southeast Asia to Taiwan. We are coming from here. And there's a 8-hour flight from here to Dubai. Okay. And very convenient. This is the first time I'm coming here. I thought that was very far away. I've never been here. But it's very smooth. Very smooth. Very good. So if you are interested in learning solar cells, actually, you know, in Taiwan probably is arguably the best solar cell producing countries in terms of efficiency. Nowadays, we are producing silicon-based solar cell with efficiency higher than 20%. That means 100 photons coming into our solar panel. There will be 20 photons successfully converted to electron and holes, and doing electricity and providing electricity. And we cannot avoid the dissipation of other 80%, but at least we have 20%. So that is highest among the highest that we can produce. If you buy the panel from China, China is largest producing country in terms of amount, in terms of quantity. Their efficiency may not be able to reach 20%, like 17 or 18. And by very special technique, Taiwan will be able to provide the efficiency around 25. But that will be cost more. I'll just let you know. All right. Okay, so if I convince you that our total solution, the final solution will be coming from the sun, then how? Actually, the simplest way is the collecting heat, right? Because we feel that if we go out in the summer, then we feel the heat. And actually, we can collect the heat and convert it into the air condition, the to cool down the temperature. It is possible. All right? But nowadays, we are using electricity. So we want to see if we can convert the solar energy directly to the electricity and connect it to the grid system. Instead of convert it to the thermal energy first, then convert to electricity. We want to convert the energy directly from the solar energy to the electricity. All right, so we need to use solar cell. And solar cell is made of so-called semiconductor materials. So we are going to introduce the solar cells from the initial material, semiconductors. All right? So please raise your hand if you have learned semiconductor materials before. Okay, put down your hand. Okay, so you might have basic idea what this semiconductor is. In material system, we usually divide this system in terms of conducting or non-conducting. We are separated then into 4 types of materials. Basically, metal and semi-metal, they are conducting. So you can use as a conducting wire, that copper wire that we are using in our everyday life. And they are insulator. The insulator is something like ceramics. We are passivating. We are insulating the system, so we are not touching the wire and being electrically shocked by the electricity. So this is insulator. And between conductors and insulators, we have semiconductors. Okay, so what is semiconductor? Actually, to define whether material conducting or not, we can use a band gap or band structure to distinguish them. For metals, they are filled valence band. All right. If you are not knowing the band, never mind. No problem. No problem. Just think about this. For the solid material or crystal material, they are electronic bands. Okay, bands like orbitals or like the driveways in the highway. Highway, you have many lanes, right? One orbital means one drive lane. So you can drive. The electron can drive the car in their lanes. All right. So there are many lanes in valence band, and also there's upper band called the conduction band. Conduction band means the electrons are not totally filled the band. They are empty spaces. They are empty orbitals, or they are empty driveways for the electron to drive. Okay. So in other words, valence bands are those driveways being blocked, like you encounter the traffic jams. Have you encountered the traffic jams in Oman? No, I never think about that. You have very good, very advanced highway system. I noticed that. But in Taiwan, every day we park our car inside the highway and stop there, waiting for 1 hour and drive. Oh, very difficult, very terrible. Okay, so there are pathways filled by the cars, so no car can move. So this electrons is bound between two atoms. They cannot move. This is called covalent bonding. All right, and only for those electrons filled in the conduction band will this electron be conducting the electricity. Because even though at the bottom of the conduction band there are still filled electrons, but there's always empty spaces, empty pathways for them to bypass the other car. So as long as they are now real temperature can excite them to the empty pathways, so they can conducting. If there's an electric field, they will conducting. They will move back and forth at the vacant orbitals. Okay, so they become conducting. So for the metals, what is the metal? What the metal is, because the metal, they call metal because the electron of this element is partially, not fully, partially filling the conduction band, not fully cover, not fully occupy the band, partially occupy the band, so there's still vacant band allow them to move back and forth. So it is conducting. In terms of, we explaining the conductor in terms of the band structure. All right? For insulators, something like this. It's just like the band, the valence band is fully occupied the electron. It depends on the crystal structure of the element. For some element, it just fill out, the electron just fill out the valence band. So no electron can move back and forth. So they become covalent bonding. All right? And there's no electron feeding up to the another band. So there no electron can excite to conducting the electron. So it behaves as insulator. Okay. Now, what is semi-metal? Semi-metal is something like they fill the band, valence band, and nothing on conduction band. However, these two bands overlap. So they look like one band. So even though they have electronic band structure like insulator, but since these two bands are overlapping each other, they behave like a conductor. Exactly, you cannot tell from the first perspective, it's just exactly the same as conducting materials, as metals. All right? All right, this is semimetals. And this is called semiconductor. Semiconductor's band structure is almost the same as insulator. The only difference is like the conduction band edge and the valence band edge is so close together, very small. The distance between the conduction band edge and valence band edge is only very small energy gap, so that even kT, our temperature, provides 3 seconds of the energy that will easily excite the electron from the valence band to the conduction band. So very small amount of electron will be able to sustain at the conduction band edge. So it's conducting. But it's not as conductive as the metal. So we call it semi-conducting materials. All right? Okay. And actually, the band of the semiconductor, how small, then we'll be able to call the material semiconductor. Usually, we'll say if the band is less than 5 eV, eV is the energy unit. If that is less than 5 eV, we call that a semiconductor. All right, 5 eV. And there's a conversion equation from eV to joules, but I will not mention here. But eV, you can check by yourself to see what the conversion coefficient between eV and the joules. Huh? How much? Do you know? eV wants 1 electron accelerated by 1 volt of difference. 10 to the minus 19th, exactly. Yes, very good. Okay, this is a periodic table for the elements. I just want to show you, say, from the left side, they are metal, right? They are inarguably the metals. They are conducting. But where is semi-metal? Semi-metal will be somewhere near there. Their electronic structure will be very similar to non-conducting material, insulator, but somehow they are overlapping each other, so they behave like metal from the conducting perspective. Okay? And where is the semiconductor? Semiconductor is also here. Silicon, germanium, and sometimes if you doing the compound semiconductor, it will be gallium arsenide. Combine this element with this element, it will become semiconductor again. So the semiconductor element will somewhere near this area. Group 5, group 6, actually this is group 3. Group 3 means they are minus 3 charged. Okay. Plus 3, for example, plus 1. Boron, aluminum, gallium, they are 3 plus charged, right? If they are ionic. And this is group 4. Group 4, they have 4 valence electrons outside the outermost orbital: carbon, silicon, germanium, tin. And they are group 5. Group 5 means there are 5 valence electrons at the outer orbitals: nitrogen, phosphor, arsenic, antimony. Oh, these are semiconductor materials. Okay. Now we are going to talk about the carrier concentration. That means how many electrons will we be able to know inside the semiconductor? We are going to use semiconductor, right? So we need to know how many carriers if inside the semiconductor. So I redraw the band diagram for the semiconductor. Okay, so semiconductor means the conduction edge, bottom edge, and the valence top edge are very close to each other. So that KT will somehow help portions of electron excited to the conduction band and do the conducting work. Right? All right, so we need to know how many electrons will be here in the conduction band that helping the conducting. So it will be a function of the band gap. Band gap means the gap between the conduction band edge and the valence band edge, right? So we will give you a question to relate the concentration to the band gap. Okay, so but before that, we are going to tell you an idea called Fermi level. Fermi level is where the electron or carrier occupation probability is 50%, 50%. That means that also means the average electron energy level, the highest electron energy level. All right. As I told you, may not understand. I will go into the detail. Fermi level is the average energy level of the highest electron energy. That means, I told you that at room temperature, like right now, we are in 25 degrees Celsius in this room. We have KT that may helping us the electron to excite it from the valence band to the conduction band. Not every electron, but portions. Maybe a small portion, but some will get up to the conduction band, right? But what if the temperature now is at 0 degree Kelvin, which is minus 233 degree? At that time, there's no KT helping us. So there will be no electron be excited to the conduction band. So the number of electrons on the conduction band will depend on not only the band gap, but also the temperature. Yes. All right. So the Fermi level is where the average of electrons goes to. Let me show you. You probably still don't understand this. Let me show you what is a Fermi level, Fermi direct distribution. Fermi direct distribution have equation on the previous page. At temperature equals 0. At temperature equals 0, the Fermi direct distribution will be 1 below the Fermi level, but 0 above Fermi level. All right? But as temperature increases, the Fermi level will change from the step change of this curve to a smooth curve. That means below the Fermi level, the occupation probability will still almost close to 1, except those very close to the Fermi level. All right? But above the Fermi level, the occupation probability will very close to 0, except those very close to the Fermi level. This change is because of thermal energy. The thermal energy will change its profile from the very strict 1, 0 to more smooth deviation. That means it excited some energy, it's some electron with energy very close to Fermi level to a higher energy level. All right? So this is the Fermi direct distribution function, which is a function of temperature. So if we go back to the diagram, Fermi level is where the occupation probability always equal to 50%. that is this point. The average, no matter where your temperature changes, here, the occupation probability is always 50%. So, in other words, that is where, when the temperature drops to 0 degree Kelvin, the highest energy that electron can get. All right? So it is like the sea level. It's like a sea level. When there's no wind, it's very flat. All right? Wind means temperature. It's very flat. But there's a wind coming up, we have waves. We have waves going up and down. We can find water above the water level, and also some vacancies below the water level. But in average, it's still the same, because the water amount is the same. So Fermi level is just like the water level of the electron sea.
No matter the temperature.
No matter the temperature, exactly. Exactly. Temperature like a perturbation or disturbance for like wind for the sea level. Although there's disturbance, but average is the same, no matter how much the disturbance are or amount of disturbance. So, where is Fermi level? Where Fermi level usually is in the middle of the band gap, because if you later on we'll talk to in more detail. If you excited one electron up to the conduction band, that means you have vacancy leaving in the valence band. So they all have equally amount. So from this relationship, we will know the distribution probability at 50% will be exactly at the middle, or very close to the middle of the band gap. All right, so this is Fermi level, which is called you can understand the Fermi level from two perspectives. First is from the occupation probability. That is where 50% occupation located. And also, you will be able to understand from the energy. That is highest field electron energy level at 0 degree Kelvin. All right? Okay, and I just show you the equation here. You can write it down. Actually, you will have the handout, so don't worry. It will be coming up soon. Okay, and by the discussion, we will have the equation. Since we have a very concentrated course in the following 5 days, so I'm not going to detail about the deduction of this equation. You just try to memorize or understand this equation. The concentration of electrons or holes is equal to something that can all be known. The temperature we can measure, right? The equivalent mass of electrons, actually we can measure from some other technology. This mass of electron or equivalent mass or effective mass we can measure. This is a material property. And this is Planck constant, we already know. So this is something we already know. And it is a function of exponential Fermi level minus EC. EC means the bottom edge of conduction band. So EF minus EC is, this is EC. EC means conduction band edge. This is EF, where the Fermi level located. The difference between the EC and the EF. All right? So usually we can write it down as NC. NC is effective density of state times occupation probability, expressed as E to the power of minus EC minus EF over KT. So KT is at the bottom of exponent. As temperature increases, then ending, and not will increases as well. All right? Okay. So, according to the schedule, we should have a break at 9:30, right? So, we might just have a break now. Then, in the break, we'll see if the lecture handout already available. Okay. So, I hope that after 15 minutes, the handout will be available. Okay. Now, let's take a break.那个你可能叫那个阿巴杜来带你去把那个聚光型的那个拿过来，好，拿来这边。对对对对。那个盒子吗？那个就是没有那个你聚。What did he say? Okay, now let's continue our lecture. So now you understand this equation, right? This is the concentration of electrons. Concentration electron at certain energy difference between Fermi level and the conduction band edge, and also as a function of temperature, right? So temperature, when temperature is higher, the NO will be higher. The electron number will be higher, right? So where is the electron coming from? Where is the electron come from? From the valence band. From the valence, if we want to excite one electron from the valence band, then we're leaving, once the electron being excited to the conduction band, we will leave a hole, an empty space at the valence band. That empty space we call hole, the hole. All right? So we will be able to construct another question. Hole, number of holes is exactly the same as the number in number, the same as number of electrons. All right? So number of holes will be the equation in this format. Almost the same as this one, except the distance will be between valence band edge and the Fermi level edge. All right? Okay. And the previous, and the term ahead of the equation will be so-called effective density of states. Everything inside here. Whereas the mass here is effective mass of holes, because hole will also move in the field, in the electric field. Hole is positively charged ion, even though there's nothing inside the holes, but hole is charged. It's charged. It's charged, so it will move along the electric field. So the mass is determined by how fast it will move under the effect of the field. So we'll be able to tell, even though there's nothing inside, it is called the effective mass. It looks like a particle with certain mass that move in the electric field. So they have a mass, effective mass. This is called effective mass of holes. And it also is a function of band gap, but it's portion of band gap, the distance, energy difference between valence band edge and the Fermi level. And it is also a function of temperature. All right. We need to mention about this is because Fermi level, I mentioned about previous, Fermi level is located very close to the center of the band gap, right? Right. But somehow Fermi level is not always there if we do the doping. I'll mention about the doping later on. Now we are discussing about the semiconductor without doping. That's pure, not contaminated, pure semiconductor. The Fermi level is located very near at the center of the band gap. Okay, so from the equation, here we have the equation like this, right? Now we take these two equations to the next page. We'll have Ni. Ni is actually N naught at intrinsic. Yes, please distribute the file now. Oh, some colored version, black version. You are lucky. Maybe this is for lecture. Now we are going to page 8. You can go to page 8, so we are at the same page. Page 8. Okay, so everybody should get the handout now. So who haven't got the files yet? Oh, it's coming up. Oh, I can go ahead now? Okay, so wait for just a few minutes. Okay, so I'll start the presentation. So we got the equation. The equation is still a little bit different from the previous page. You see? This is N naught. N naught. N naught means no doping. That means I'm using the pure semiconductor without putting any other element or other contaminants. All right? So when the Fermi level, so at that time the Fermi level will be at the center, at the middle of the band gap. We call that EI. EI means intrinsic. Intrinsic means we are not doing the doping. And that is opposite to the extrinsic. Extrinsic means I'm doing the manually doing the doping. So this equation actually is a general equation. So when there is no doping, we call Ni. We call the concentration Ni, which is Fermi level equals EI. As this one. Okay, so Ni is when Fermi level is exactly at the middle of band gap. We call that EI. Because Fermi level can be adjusted, but I will show you later. All right? But when the material, semiconductor, is not doped, EI is located. EI is located at the middle of band gap. Okay? And this is basically the same as previous equation. And later on we'll show you when Fermi level is changed by doping, then sure, the number will change, right? Okay, for intrinsic semiconductor, which means non-doping, then we have previous equations, right? Then we know when the semiconductor is not doped, the number of electrons will always equal to the number of holes because electrons are activated by the electrons previous at the valence band. So once it's got excited to the conduction band, they will always leave the holes in the same number at the valence band. So Ni will always equal to Pi. So we can equate these two together. Then we will be find out the intrinsic Fermi level with respect to these variables. All right? EC, here, EC and EV EC is conduction band edge. EV will be valence band edge. So if we combine this, equating these two together, we will be able to find out the location of EI, which we almost already know. It's almost at the band gap, the center of the band gap. But actually, it's not exactly, because you see, if EI equals EC plus EV divided by 2, that will be at the center. However, from the deduction of this equation, since it is also related to the effective mass, that is related to the orbital, the shape of the orbital. So that's slightly different, but it didn't account too many, because this one will almost the same as this one. So long 1, if the NV equals NC, long 1 will be what? 0. So this term actually is almost close to 0, especially when temperature is very low, then this is insignificant. So basically we know it's about at the center of the band gap. But if you want to know very precise in number, then you need to calculate. MV and C is related to MP and NN, which is effective mass of electron and effective mass of holes. This is the exact expression of the equation. Okay, so we have the equation for Fermi level without doping. Then we plug this equation back to the previous equation, we will be able to get the final expression of the number of electrons or density of electrons at certain temperature and at certain EG. EG is EC minus EV, the difference between conduction band edge and the valence band edge. So this is the final equation. All right? So now I rewrite this equation to the next page. All right? So we want to know how temperature affects the concentration of intrinsic semiconductors. So we need to find where will be the temperature appear in this equation. Here's one, and also is in the power of exponent. All right, which will dominate? Is the exponential term or the power term? Exponential goes very fast. It's much faster than the power, the regular power term. So this will dominate. All right. So actually, Ni changes with T, but how? Exponential term dominates. All right. So let's take a look of the relation. I put the relationship again in this page, and here on the left side, this is the exact measurement of Ni versus 1 over T, inverse of temperature. So this is just like if I take this, you see, this is a log scale, right? Log 10. So if I take this log, then it will showing 1 over T dependence, the linear dependence on 1 over T, inverse of temperature. If I take the log, this will be a constant. And the take log, then the power term, the exponent term will be linear too. So it's 1 over T. So if you take this log, take log with respect to 1 over T, the concentration will almost be linear related to the 1 over T. All right? This shows, this is proof that Ni is actually dominated by exponential term. It's not dominated, it's just like a constant. Otherwise, it will not look like a straight line. All right. From the straight line of this relationship, we'll be able to tell this equation is probably right. Okay. And also, we have 3 different semiconductors, germanium, silicon, and gallium arsenide. And we have, for certain temperature, at the same temperature, germanium has higher electron concentration than silicon and gallium arsenide. That is because it's band gap. You see, in this function, there are also concentration of carrier is also a function of Eg. What is Eg? Band gap. Band gap is energy difference between the conduction band edge and valence band edge. Ec minus Ev. All right? So it is also a function of Eg. So with smaller, because it's minus in front, so with smaller Eg, there will be higher Ni. So germanium has band gap about 0.67 eV. This is known value, material properties. So it has highest among these three semiconductors, high carrier concentration. And silicon has 1.11 eV, so it has middle value among these three of the carrier concentration. And gallium arsenide has highest band gap value among these three, so it has lowest carrier concentration. And this can be understood intuitively, because with wider band gap, it's more easy or difficult to excite electron. Difficult. With wider band gap, it's more difficult to excite it. So only small portion of electron will be excited at the same temperature. So for wide band gap, it has less electron concentration for the conducting in the conduction band, and also the same number of holes in the valence band. Okay. And it also changes with temperature. The x-axis, the temperature axis is actually 1/T. So which side is high temperature? Left side is high temperature, or the right side is high temperature? Left side is high temperature. Yes, it's 1/T becomes higher on the right, means temperature is lower. So lower temperature got very low concentration, while high temperature got very high carrier concentration, right? Okay, so we finish the intrinsic semiconductor, where the Fermi level for intrinsic semiconductor is located near the center of the band gap. Now, I'm going to talk about Fermi level can be engineered. We can change the Fermi level of the semiconductor. Okay, so I talked to you about this Fermi level where electron occupation probability is 50%, or the average of the highest average energy level of highest electron energy. It's maybe a little bit difficult, but you can think about the average Fermi level is where the level for the electron with highest energy in the material system. Okay, for the undoped, that means without, say, pure silicon. In pure silicon, the Fermi level will be almost at the middle of the band gap. So right now I'm not drawing the whole structure of the band. I just draw 3 lines. So in the textbook, you'll find this representation. Always draw 3 lines. The first line is conduction band edge. Actually, it's not just the energy level, it's the bottom of the conduction band. And also, there's bottom line here. It's not just a line, energy level, it's the top portion of the conduction band edge. So this is simplified representation of band gap. And we'll draw the Fermi level. For the undoped semiconductor, the Fermi level is at the center, close, very close to the center of the band gap. Now we're defining two terms. One is n-doped semiconductor, negatively doped, negatively charged doped, and the p-doped, positively doped semiconductor. We simplify it as n-doped and p-doped semiconductor. N-doped means we are generating electrons more than holes. And p-doped means we are generating holes other than electrons. And the Fermi level will increase to above the previous. Actually, I should write this as EI. I can also write this as EI. EI means the Fermi level for intrinsic semiconductor. So for this one, I can change this as EI. But other than undoped semiconductor, we will always write EF. Okay, so why, when we doped something, we'll be able to change the Fermi level? Huh? Yes, please.
Doping causes either to have more electrons or holes. So
Yes.
Make the electrons
More prone to excite to the electron. Very good. I think you have a background for semiconductor doping, so very good. I'm going to talk about exactly what you have talked, right? So this is silicon. I just use silicon as an example. Silicon has 4 valence electrons. 4 electrons at the outermost orbitals. And this 4 electron is shared with 4 neighborhood silicons. So each silicon atom will provide 4 electrons. And this 4 electron is shared by neighboring silicons. So it forms exactly the same of a covalent bond. 2 electrons from fill in an orbital. So it's bound very tight. So it will be very difficult for them to excite the covalent bonding, the electron in the covalent bonding from the valence band to the conduction band. So for pure silicon, it is almost non-conducting. There may be a slight electrons, but very little. So silicon is not conducting, pure one. It's covalent bonding. However, it's very difficult for us to get the pure silicon. It's very expensive. So when you have silicon, it's always contaminated. So it's kind of semiconducting. All right. All right. So for this silicon, if there's no contaminants, contaminants sometimes is not bad. Determined by how you contaminate it. If we purposely contaminate this one and fulfill our purpose, it may be good, right? So at that time, we are not to talk about it as contaminant. We say doping. For undoped semiconductor, we require EG. This is band gap to excite electron in the covalent, strong covalent bonding to the conduction band. EG is quite high because silicon band gap is around 1.1 eV. So with this need energy to excite. Then do you know the KT? What is KT value in terms of EV? KT is 0.0259, something like that. Something like that. I want to see if I have this value. Zero 0.0259, right? Here. This is KT, the order of KT. So it is much smaller than the band gap of the silicon. Band gap of silicon is about 1.1 eV. So it's much smaller. However, will this energy excited some or portions of electron of silicon to the conduction band? Still, it is possible. just like we have distribution. Our average, this is ideal average. The KT, the average of KT at room temperature, KT, T is 25 degrees Celsius. That means 298 Kelvin. This is the average of the temperature, energy of temperature. However, when you say room temperature, does every molecule the same energy? No, the distribution. Just like our society, there are some perform very good, some perform very poor. Their distribution, but average is this number. All right. So even though the average KT is in this order, there will be high energy that will excite some portion of the electrons of silicon to conduction band. All right, but just be very little. All right. Now let's back to this page. So if you have energy higher than Eg, then you will be able to excite the electron from the valence band to conduction band. I will show you here. Take a look of this electron. I will excite this electron to another atom. So I'll give you energy larger than Eg. Then this electron got excited to another silicon, neighboring silicon, leaving a hole, yes, or a vacant orbital in the previous silicon. So in the energy diagram, I'm sorry, here, can you see? It's difficult to see that. We excite the electron to the conduction band edge, and we're leaving a hole as a valence band. Okay, and both two type of carrier is conducting, but just move to different direction. All right, in the field. Hole is positively charged. It will move along the field, and this electron is negatively charged, so it will move against the field. Okay, but so if you want the material to be conductive, you need to create carriers. And when you want to create carriers, you want to have a thermal energy or any kind of energy that can excite, have an energy higher than its band gap. Then you will be able to excite the electron and holes. All right, now let's go to Undoped semiconductors. Undoped semiconductor is to contaminate very little amount, maybe only one. You see, it's not silicon anymore. Here is phosphorus. I just use phosphorus as an example. It's group 5. So in its outermost orbital, there are 5 valence electrons. 5 valence electrons. So I dope phosphor inside the silicon. Very little amount. It's just like I dope 1 in 10,000 of silicon, or millions of silicon. Just one, very small amount. Right? So if I dope this phosphor in very little amount in the silicon crystal, it will not alter the silicon structure. Phosphor has different, if a pure phosphor has different crystal structure than silicon. However, if I dope very little amount, then it's just like dissolve. It's just like dissolve in the crystal structure, in the silicon crystal structure, without altering the crystal structure of silicon. So it's still remaining the silicon crystal structure. However, it changed the electron state. Okay? So if I put phosphorus in the silicon crystal structure, then phosphor has 5 electrons. So since it is in the silicon crystal structure, it still have 4 neighboring hood. So it shares 4 out of 5 electron with 4 neighboring hood. But there's 1 extra electron. This electron will still staying near the phosphor to remain the electron neutral. All right, this one is still staying here because phosphor they need 5 electrons outside. So this electron will stay at the orbital of phosphorus. Then it's electron neutral. All right.
To stay at
Stay at the phosphorus orbital. Then it's electron neutral. It looked like not symmetric because you feel that there's extra electron. But that is not extra because phosphor need to have 5 electrons in his outer shell. So it still need to stay with phosphor to keep electronic neutral, right? But however, your intuition is correct. This look like extra one in the silicon crystal structure. That means this electron is different from other electron. It can be promoted or excited more easily than the rest of electron.
Yeah, it's a free one.
Yeah, you can feel that, right? It's in the crystal structure. It's not symmetrical, so it's different from other electrons. So for this electron, it can be excited more easily to the conduction band. All right? So we can draw the energy level of this kind of electron. Definitely, it is more close to the conduction band, right? More higher than the intrinsic level, but more close to the conduction band. It has to be that way. Although that means this one is easier to be promoted. Okay, so I'm not going to the exact value, but I just show you the idea that if I doped group 5 element in silicon, group 4 crystals, we will be able to create Fermi level going up close to the conduction band. Okay? Then that means right now we don't need to have energy Eg to excite the electron. We don't only need a small amount of energy to excite the electron to the conduction band, right? Yeah, it's exactly what happened. But we didn't create hole. We didn't create hole. We only create electron. All right, so for this case, the number of electrons will be much more than the number of holes. This is called Undoped. Okay, so take a look up here. I excited this electron to other silicon atoms. And we found out this now phosphor is exactly the same as other silicon, but other silicon have 1 extra electrons. This has become conducting electron. It can go everywhere as long as it still remains its energy. All right? Because once it gets away from phosphor, it becomes unstable. It will keep its energy. It can until it finds another phosphor atom. Otherwise, it will move along. It becomes free electron. Okay, now here goes here, and there's nothing inside Fermi level. You create the electron at the conduction band.
Without hole.
Without hole. Without hole. Yes. Okay. Now we move to p-doped. Same logic. Same logic, but different doping method. Now we are choosing element with less valence number than silicon.
To create hole.
Yes, like holes. All right, so the same way of explaining this, if we boron or aluminum, you can choose any one in group 3. boron. If we dope boron in the silicon crystal structure, since boron has 3 outmost valence electrons, then they need to share with 4 neighbors. So there must be 1 neighbor without electron. It seems like there's lacking 1 electron, but actually it's not, because boron only needs 3 electrons outside. So this is the neutral structure of the doping structure. This is neutral. Nothing wrong with that. Nothing wrong with that. However, if you take a look, it looks like there's 1 electron missing. Actually, it's not. It's exactly the same. Look like electron missing because this boron is different than the rest of silicon. So it looks like it's inside the crystal structure. So it looks like it's missing. That means it's very easy to have electron going into this side without any high energy. Just small energy dissipation. We will allowing another electron from another atom to go to this side. All right? So, so that means it looks like there's a space in this area. And I only need to use a very small energy. We can excite previously valence electron to this position. So I will get holes at the valence and be conducting. Okay. So take a look at this electron. Take a look at electron. I will excite this electron to the boron. Okay. Here. Take a look here. And now this can be represented by in the energy diagram. That is, I excited 1 electron to the Fermi level. Then Fermi level becomes the same structure as other silicon, so didn't have holes in here. But I create a hole in the valence band, and it becomes conducting. Okay, so now the conducting material for p-type dope is hole. All right, so it will move at the valence band. Hole actually is it's not a particle. It looks like a particle, but actually it's nothing. So how hole move? That is, hole is moving by excite another electron to the location. So the hole will move to the place that the electron was activated.
It's like a ghost.
Yeah, looks like a hole is moving. Actually, it's just replacements of the electrons. Okay, so now you know the N-doped and the P-doped semiconductor. That is a very, very important progress because I'm going to show you the carrier concentration variation with temperature. Again, this diagram shows N concentration versus 1 over T. So which side is low temperature? Left side or the right side? Low temperature. Low temperature. The number is very big for 1 over T. So it's low temperature at the right side. Low temperature at the right side and high temperature at left side. Right? So at very low temperatures, sure, they are very low KT value.
Depends on what
So there will only be possible activating the doped electron. Say this is for doped semiconductor, right? It will only be able to excite the electrons at the doped semiconductor. So it will create the electrons. And this electron number, it actually is fixed by what the concentration that you are doing the doping. It can excite it more than the concentration you are doping, because each dopant creates 1 electron. So the total electron that you will be able to generate is exactly the same as the concentration of doping. Understand? I'll try to let you know. Okay, so now, so for the low temperature, if you don't have temperature, you still cannot activate the electron at the Fermi level, even though you have doping. So at very low temperature, you are increasing the carrier concentration with respect to the increase of temperature. Okay, until you excited all the dopants. Then you have a so-called extrinsic doping concentration. That means your concentration is controlled by your artificial doping. You're doping artificially. It's not controlled by its intrinsic property. You are creating a carrier concentration by artificial doping. Okay. So now, if you excited all the dopants, you will maintain a same concentration value of electrons. Even though you are still keeping increasing the temperature, you are not significantly increasing your electron concentration. Why? Because all the electrons in the Fermi level are excited by your thermal energy. All right? Now, but as the temperature increases, the kT increases to certain high temperature. Eventually, you'll be able to excite the electrons at the valence band again. So at certain temperature, the exponential will increase and to generate electron higher than your extrinsic level. Then you become intrinsic materials. All right? Okay. So we call this intrinsic again. At that time, you can not increase the extrinsic doping because the doping is fixed by how much the concentration that you doped. So at very high temperature, even this silicon is doped. It's still called intrinsic because extrinsic doping is insignificant at high temperature. All right, so the concentration profile will be something like this. At low temperature, excited extrinsic doping, and very high, even higher temperature, it will activate the valence electron and become intrinsic again. Okay. So let me ask you some questions, just make sure that everybody understands this idea. What will be, okay. So for example, at this temperature, at 1 over T, 1000 over T at 12, at this temperature, most of the conducting electrons are coming from dopants or the valence band of the silicon. At this low temperature, most of electrons are coming from two possible places. One is from the dopant that you dope phosphor in silicon, dopant, or the silicon itself. Okay, so raise your hand. First one, if you think the dopant is, the electron is coming from the phosphorus dopant, please raise your hand. Now, maybe I didn't repeat the question. At very low temperature, like this place, this is low temperature, right? The electron may come from two places. One is from the dopant atom, like phosphor, okay? and one is from the covalent bonding of silicon. Okay, so where is most possible that electron coming from? Yes, I just want to raise your question. If you think from phosphorus at low temperature, most of electron coming from phosphor, please raise your hand. Okay, put it down. If you think the electron is mostly coming from the covalent bonding of silicon, please raise your hand. Oh, put it down. The correct answer will be coming from phosphorus. At low temperature. But this is very important, so I want to spend more time with you. At low temperature, this is phosphor-doped silicon. We don't need many energy. We don't need that large amount of energy to excite electron to the conduction band. All right? So we put our Fermi level very close. It's a behavior. The Fermi level have to be very close to the conduction band. So we don't need a very high thermal energy to excite electrons. We only need to provide the energy between conduction band edge and the doped Fermi level. All right. So at low temperature, we will be able to excite the electron from the doping element to the conduction band. So most of electron is coming from the dopant, or the phosphorus. All right? Who still don't understand the idea? Please raise your hand. Okay, put it down. Who understand what I'm talking about? Please raise your hand. Okay, put it down. Now it's better. So at these low temperatures, we have electron. This is a profile of a carrier. In this case, undoped case, that is electron. With increasing of temperature, that means we are moving towards the left. The concentration increases, right? The concentration increases. That means when the temperature increases, to a certain point, I will go to a temperature energy that is higher than the difference between EC and EF, right? So I will activate all the dopants. So as temperature increases, I'll be able to increase the concentration of electrons until all the dopants are activated. So the electron number will stay the same, even though I still keep increasing the temperature.
Why does not change?
Huh?
Electrons from 10 to 2. Why there is no change?
10 to 4, right. Almost no difference. Actually, that's different because for intrinsic, there's also exponentially increases, right? But at this low temperature, this profile is insignificant. So it looks like the profile, this concentration profile is constant along the temperature. It's because at this temperature, it will be only excite electrons from the dopant. So for example, you doped only 1 out of 1,000 in the silicon. And as temperature increases, once you excite all the dopants, then even though you increase the temperature, you'll still not be able to activate those electrons at the valence band. You just excited all the electrons in the dopant, on the dopant atoms. But that's all. So in certain temperature range, you will be able to get constant carrier concentration without change with temperature. All right? Then as temperature goes higher, very high, maybe 1000 degrees, then eventually you have more energy. Then it is possible for you to excite those electrons at the valence level, then go into the conduction. And as temperature goes higher, this number may exceed the doping concentration. So the number will pass the extrinsic doping level and become intrinsic. How about that? Please.
I have a question. Since you are saying that we need temperature so we can get the motion of the electrons, so we can get current.
Yes.
Then why the PV panels, the efficiency decrease once the temperature...
Wow, you are going to talk about something that I'm going to show you tomorrow. It's because the conductivity is controlled by two factors. One is concentration, carrier concentration. Other is temperature, phonon disturbance. Because at high temperature, you have random vibration of atoms. That will interfere with the transport of electrons. So that dominates the carrier concentration. So the conduction decreases. Yes? Temperature and density of the temperature. Density, what is the density of temperature? Yes, but we are talking about at equilibrium concentration. Say the temperature is constant everywhere. So if there's a temperature variation place by places, then the semiconductor will perform differently. So at higher temperature, it may perform poor. At low temperature, it will perform very good. However, if you cool down the semiconductor at 0 Kelvin, then will it efficient very good? No, no. So there will maximum good temperature for you to operate, right? You cannot cool down because if you cool down to very low temperature, there's no electron concentration. Then there will be no conducting. Even though you reduce the vibration, interference vibration, you also reduce the concentration of the carriers. So you finally got nothing. So there are good temperatures for you for the solar cell operation, right? Okay, so probably you can understand this now. If not, then discuss with your classmates, all right? Okay, so we have NO. This is I just copied from the previous pages. NO means this is a general equation for whether it's intrinsic semiconductor or extrinsic semiconductor. Intrinsic means I'm not doping anything. For extrinsic semiconductor, that means we are intentionally doping the semiconductor. So this is for general equation. EF can be anywhere in the band gap, all right? But this one is just rewrite of this equation, but put EF as EI. EI means no doped, the Fermi level for non-doped or intrinsic semiconductor, which is very close to the center of the band gap, all right? So we can write down this one. And since these two equations are very similar, I can use N naught as a function of Ni, right? I can divide the N naught, divide this equation by this equation, then we will be able to get N naught is equal to Ni times exponential. Oh, the difference between the Fermi level of doped semiconductor to the Fermi level without doping. So we'll be able to get this one. Ni is the intrinsic concentration for intrinsic semiconductor, and NO will be the carrier concentration with doping, and NO will be always higher than Ni. NO will usually, I should say more conservative, usually higher than Ni, because EF is always higher than EI for N-type doping. N-type doping. But for P-type doping, hole will be also higher than this one. That means its EF is lower than EI. So we have hole concentration, right? Okay, now I want to show you another question. I want to compare NO with Ni. Actually, it's from this question. I want to compare EF and EI. EF is Fermi level for doped semiconductor. Compare with EI, that is Fermi level without doping. Okay, so I just rearrange this equation. Then I will get this equation. Oh, the Fermi level, the location of the Fermi level for doped semiconductor is where the Fermi level for intrinsic semiconductor plus this term. Plus this term. So, so we can measure the concentration. So we'll be able to predict what is the height of Fermi level by measuring the concentration of the semiconductor, compare with intrinsic concentration. Then we'll know the location of Fermi level.
That's okay.
Okay, so by this equation, we'll be able to know the Fermi level or P-doped semiconductor is actually increases with the carrier concentration. And usually we will operate the semiconductor at which region? Intrinsic region or extrinsic region? Extrinsic. We want usually, for this one, we want our room temperature something in the range of intrinsic region. So we can control the doping concentration, and we can control the carrier concentration, right? We don't want go at this area, because at this area, it behaves like we are not doping anything. So our work is in vain. So we are not operating this one. We are not operating at this one because the carrier concentration still increases with temperature. So if there's a temperature fluctuation, then we don't know the carrier concentration. So we want to operate at this one, at this region. Okay. So here we use doping. That means we always operate at extrinsic region, so that we will be able to know the carrier concentration. It's exactly the same as doping concentration. All right. How much you dope is how much you have carrier concentration in the conduction band. So with doping concentration increases, you will be able to control the Fermi level at the conduction, in between the conduction band and in between the conduction band edge and the valence band edge. All right, and for holes, for P-type doping, you'll be able to control the Fermi level corresponding to the boron or hole doping or P-type doping concentration. All right, so you can control. Once you can control, you'll be able to control the property of semiconductor. I shall show you later how we do the solar cells, how we design the solar cell. All right. So actually, this is another schematics of the band diagram. the top portion is conduction band. There's no electrons fitting inside the conduction band. There's field electron in the valence band. The bottom portion is valence band. The top portion is conduction band. All right? When you do the doping, you will artificially form a band inside, in between the conduction band and valence band. It's here. So this is more close to the conduction band. So this is N doping or P doping. N doping, yes. If you are doing the P doping, you will find the defect level more close to the valence band, or compare with the level at the middle, right? So you will form a defect band closer, move from the center towards the conduction band edge. Okay? Now, as the doping concentration increases, so we'll be able to move the Fermi level more closer to the conduction band edge, right? That's exactly what happened. And also because the temperature, it will get the vibration of atoms. So this defect level will also a little bit expand. You see? A little bit expand because it will add the KT vibration. So its band actually increases a little bit. So as the doping level increases more, say like to 10 to the 19th, it will be very close to conduction band. So at this time, you probably all the electron can be excited. Oh, that means you've got very high concentration of electrons. Okay, so I will go to another extreme. When the doping concentration is very high, like to 10 to the 21 or 22 per centimeter square, if you put that high amount of dopants, you will cause the overlapping of the defect level with the conduction band level. And actually, you will change the shape of a conduction band. And at this moment, you will see it's overlapping. So it looks like the band have some field electrons. So it behaves like metals. It's conducting. So it is not semiconducting anymore. So we call this situation degenerated semiconductor. It's not semiconductor anymore. It's conducting. So this is very important material. This is very important material, saying that usually we have ceramics with non-conducting. However, if we dope a large amount of dopants, it became conducting. And it's still transparent. Usually metal is not transparent. But nowadays we want to do something. We want to make something that's transparent while it's conducting. For example, our solar cell. Our cell, we want the light to be transparent to the mirror, to the solar cell, so it can shine the p-n junction. However, we want it to be conductive, so electron can be conducted out. So this is the way that we are doing transparent conducting materials. Transparent conducting material can be used in the TV or the LED lighting or the imaging. We need the light to pass through the medium while it is conducting. So usually we use this mechanism instead of using metal. Metal, although it's conductive, is not transparent at all. Okay. So we call this degenerated semiconductor. The degenerate semiconductor is actually Fermi level higher than the conduction band, because conduction band drops because the overlapping of the defect level with the conduction band. And also for degenerated p-type semiconductor, the Fermi level goes below the valence level. Okay, so today I finished first portion of the p-n junction. which is semiconduction part. So tomorrow I'm going to continue from here. Tell you now if we combine p-type semiconductor with n-type semiconductor, what will happen? We are going to form the p-n junction. Right? Okay, now take a break. And we are going to use this time to move to the lab. So we are going to conducting the lab in other places. Right? And also, I'm going to show you this piece. What does this look like?
Lens.
Mirror. But actually it's lens. But it's not, it's flat. It's flat, right? And it can focus light, you see? And it's very light. It's not heavy because it's very thin. Okay, we can do it thinner. We can make this like this one. All right, it's still focusing. You see? Okay, you see? You see? Okay, for some reason, for some certain solar cell, if you focus the light in the chip, the efficiency increases. In efficiency, not the power. Power will always increase because you focus the intensity. The power will always increase, but in efficiency always increases. That's very strange, right? This type of solar cell called concentrated solar cell. And we are going to talk about probably in the 3rd day and the 5th day. Okay, so it's new technology for the solar cell. And later on, Dr. Dr. Zhang will show you at the lab using this one. Even though we haven't touched upon this one in the lecture, but we will show you later. Okay, now let's take a break.
So the next issue being lab, being one next to the maybe you can grab something while you are going there. There's some packages up there, and there's something there. So we'll meet there at 11:30. Maybe ladies from this queue, maybe they can guide the others. One, you will be with us. Maybe you can guide the lady to the Undoped Society.